Welcome back, everyone. If you joined us for the first part of our OpenClaw architecture explainer, you know we mapped out the whole high-level landscape of this incredible local-first AI assistant. Well, today I am absolutely thrilled to welcome you to part 2 of our 6-part series. We're looking exclusively at the communication and distributed protocol. Basically, if OpenClaw's gateway is the brain, today we're figuring out exactly how it talks to its limbs. Okay, let's dive right into our roadmap for today. We're going to start with a quick welcome, then walk through the handshake process, break down the frame types, and finally wrap up with the node registry and heartbeats. First up, welcome to part 2, the nervous system of OpenClaw. Let's move right into the handshake process, establishing trust. So we're diving deep into section 5 of the OpenClaw architecture, and this focuses entirely on the gateway to node connection. You can kind of think of this as the central nervous system. The gateway is your central control plane, and the nodes are the clients sitting right on your devices, like a terminal interface, a macOS app, or even an iOS device. To make this decentralized, local-first ecosystem tick, they use a combination of WebSockets and JSON-RPC. WebSockets give us that persistent, full-duplex connection, while JSON-RPC brings in a super lightweight, stateless data structure that's perfect for invoking remote commands without the heavy baggage of traditional REST APIs. But before any real data processing can actually happen, we've got to establish trust. Think of this protocol a lot like a human relationship. Before you start sharing your deepest secrets or executing sensitive system commands, you need a proper, formal introduction. And here is exactly how that introduction plays out in 4 distinct steps. First, the node initiates a raw WebSocket connect to the gateway. Second, the gateway fires back with a challenge containing what's called a nonce. A nonce is basically a cryptographic number used only once. This is absolutely critical for local-first AI because it prevents replay attacks on your local network. Even if someone intercepts the traffic, there's no way they can reuse that old handshake. Step 3. The node responds to the challenge with its ConnectParams, and this is vital. The node passes its specific device ID, its unique capabilities, the exact commands it's allowed to run, and its platform info. It's essentially handing over its resume and ID badge. Finally, step 4. If the cryptography lines up perfectly, the gateway sends a hello OK message, complete with the active session info. Boom, trust is officially established.
Now, what's really interesting about this next slide is looking at what happens immediately after that dark gray connection established bar. We're looking at the exact sequence detailing the RPC, or remote procedure call. Now, in this context, an RPC invocation is really just the gateway asking a node to execute a specific local script or tool, or vice versa. Just look at the continuous, ongoing dialogue happening there. You've got request frames flying back and forth, response frames matching those exact requests, and event frames continuously streaming data. You can also spot the periodic heartbeat ticks down at the bottom, which we'll actually cover in just a minute. But the main takeaway here is that once that initial door is open, the gateway and the node aren't just, sending isolated pings at each other. They're locked into a constant, highly structured conversation that is absolutely necessary to run complex AI tasks across distributed hardware.
Moving on to frame types explained, the vocabulary of the protocol. Okay, so if that sequence we just looked at was the flow of the conversation, these data packets are the actual vocabulary traveling across that WebSocket connection. We have 4 primary frame types doing all the heavy lifting. First up is ConnectParams, moving strictly from the node to the gateway. Like we just talked about, this is the initial handshake, carrying the device metadata and security credentials. Next, we have the request frame, and this one is bidirectional. It handles the RPC invocation, so it carries the method being called, the required parameters, and a specific request ID. Naturally, that's followed by the response frame, which is also bidirectional. It returns the result with that exact matching request ID, so the system knows precisely which question or command is actually being answered. Now, pay close attention to the event frame. Notice its direction. It flows from the gateway to the node, and it handles server-initiated events, like streaming deltas, without needing a request ID at all. Guys, this is a massive architectural advantage for AI applications. Let's say your local AI model is generating a really long, detailed text response word by word. It uses these event frames to efficiently push those tokens to your screen instantly. It doesn't bog down the network by forcing the client to beg for a new request for every single word. This continuous stream is exactly what gives you that low-latency, real-time feel that we all expect from modern high-performance AI tools. All right, let's look at the node registry and heartbeats, keeping track of connections. So picture this. We have all these frames flying back and forth, potentially across dozens of connected nodes. Your phone in your pocket, your laptop on your desk, maybe a server tucked away in your closet. How on earth does the gateway manage all these active conversations without getting completely overwhelmed? Well, enter the node registry. It's the central manager for the entire system. Think of it as the ultimate real-time roster. It tracks all connected nodes using 2 distinct identifiers.
the node ID and the connection ID. Having both is actually a crucial distinction. The node ID represents the permanent identity of the device itself, whereas the connection ID represents that specific, temporary WebSocket session. So let's say your laptop momentarily drops off the Wi-Fi and then reconnects. It gets a brand new connection ID, but the system still completely recognizes its core node identity. The registry also stores all those capabilities and permissions that were gathered during the handshake. This is what ensures that the whole invoke and response pattern works flawlessly. If the gateway asks a node to run a local tool, the registry manages the timeout for that RPC call. And if a node just abruptly drops off the network entirely, the registry automatically handles the cleanup so the gateway doesn't waste precious processing power trying to talk to a ghost.
But that raises a big question. How does the gateway actually know when a node has become a ghost? I mean, how does it know if you simply walked out of Wi-Fi range or slammed your laptop shut right in the middle of a process? Well, that is exactly where this bold number comes in. 30. So the crucial point here is that this 30 represents the 30-second heartbeat tick. Every 30 seconds, a liveness check happens between the gateway and every single connected node. The system relies on this really vital piece of logic called drop if slow. If a node just stops responding to these 30-second ticks, the gateway doesn't just sit there hanging, waiting forever and tying up system resources. Nope, it actively drops the dead connection. This ensures that only healthy, highly responsive nodes remain active in the node registry, and ultimately, that protects the entire OpenClaw ecosystem from crashing or bogging down just because of a few unresponsive limbs.
Which leaves us with a perfectly functioning, highly communicative, distributed network. The gateway knows its nodes, the nodes are securely vetted, and data is streaming effortlessly back and forth. But here's the real question. What is actually generating all that brilliant data in the first place? Well, next up in our Explainer series is part 3, where we're going to dive right into the core AI pipeline itself, the Pi framework. How does it think? How does it build system prompts? How does it handle reasoning levels? It is a fascinating look under the hood, and you definitely don't want to miss it. I'll see you in the next part.